Welcome back for another episode of Maths IGCSE ZNotesLive, and I'm your host for today. My name's Devan, and also we have Ivan here, our expert. So Ivan, please introduce yourself.
Thank you, Devan. So hello, everyone. It's great to have you back, and for those of you who are just tuning in, my name is Ivan Zelich. I did a Masters of Pure Mathematics at the University of Cambridge, and I'm taking the IGCSE Math ZNotesLive sessions. So we're going to continue. Now I think it's our 12th episode today, and we'll be going through probability. So as usual, we're getting right into it. So to unpack, the key concepts, it's basic probability. And so there's a few different key points you'll have to keep in mind when it comes to how to apply probability in problem solving. So that'll be our focus for today. So there isn't much to it, but to just talk about the concepts as they come. So the basics of probability. Probability is the study of chance or the likelihood of an event happening. So as the second point illustrates there, the probability of an event is the number of favorable outcomes divided by the total number of outcomes. So yeah, it's a kind of the universal definition. You find the number of outcomes you're interested in and divide it by how many possible ways or outcomes and how many possible things can happen and the number of them. Probability of 0 means impossible, and probability of 1 means it's certain, and in general probabilities lie between 0 and 1. Now when you there is a little scale here, and for example when you flip a coin, it's a 50-50 chance of getting heads or tails unless the coin's somehow rigged. Of course. So there's always that possibility. But for example, if like the weight is a bit heavier on one side than the other, then it can sometimes have a higher chance of flipping that side. But anyway, it's usually meant to. When they say in the problem it's fair coin or fair dice, then
it's always fair unbiased.
Yeah. Okay. So we'll continue. Not much more to say about that. Okay. So mutually exclusive is an important issue. Essentially, what that means is basically, as I think this is a perfect diagram actually to have a look at. So mutually exclusive would mean that if you have aces and kings, then somehow if you're getting an ace and getting a king, they don't have any overlap between them. If they do have an overlap, then saying what's the probability of getting an ace or a king is not as simple as just adding the probabilities. There'll be some sort of overlap in which you must take away. So that's an important point. You can kind of figure out if you roll a dice, for example, as saying here, what's the probability you're having a 2 or a 5? You can't have 2 and 5 together, right? So that's why in this case it's mutually exclusive. But it is important to think about that before you just add probabilities as they come. Okay, so independent events. So independent just means that if one event happens, it's not dependent on the other event happening. So if you have two events, they're independent. They're unaffected of the occurrence of the other. And so then there's this AND rule, which basically says that for two independent events, the probability of getting both is the multiplication of the two. It's important to keep that in mind as well. So when you say you roll you roll a dice and you want us to roll the dice twice, then the things you get, the numbers you get on that dice, they don't depend on the previous dice. So you can multiply the probabilities of what you're interested in that case, for example. Conditional probability. So this is an interesting one. So conditional probability is probability of an event A given that another event B has already occurred. So, for example, you could have a situation where you have a probability of an event, but given some event that happens, then it's more likely that that event initially can occur, given that another event has occurred. So there was this famous instance of the Monty Hall problem, which basically had you had some doors, 3 doors, and behind each door you had I think it was like two doors had really nothing behind them, and one had a car. And I think the probability was that you selected the chance was you selected an arbitrary door, and then the guy would tell you, okay, so I'm going to show you a door that didn't have the car. So you can always do that because there's 2 of them. You can't select both. And then he asks you, do you want to swap or change your choice, or do you want to continue with the choice that you initially made? And once he shows you that one door is open, then your probability doesn't stay like a half. It's actually switching gives you 2/3 probability to get the car rather than the initial 1/3. So that's an example of how conditional probability could kind of work. But it's actually, conditional probabilities in some sense can be quite unintuitive because lots of amazing mathematicians had actually stumbled upon that fact and thought it was a half, so probability can actually be quite tricky. So if you are struggling with it, don't worry, because people did struggle with it in the past and probably continue to as well. Okay, so yeah, you can use Venn diagrams and tree diagrams to solve these sorts of problems. So the rule is that the probability of A given B is the probability of A and B on the probability of B. So basically what you see here is that kind of what's happening is that your total outcome is kind of B. That's like your total, and so this is why it kind of changes, the probability, because you go from like the total outcome being 1 to the total outcome being kind of B, and so the probability is P and B on PB. Yeah, and that's all there really is to say about that. Let's just talk about an example. So we have a Venn diagram here. So this kind of Venn diagram is in some sense saying, it's in some sense a proportion of the probability of probabilities in total. So the probability of A given B is going to be the intersection probability of A and B. So that's 2, the proportion is 2 on the probability of getting B, which is 3. So, the probability of getting A is kind of 3, but then in the context of having B, it would be then 2 on 3. 2 on 2 plus 3, which is 2 on 5 kind of thing. So yeah, that's kind of how it works. So yeah, it would be 3 on 3 on 10, because there's 4 here and the total number is 6. So 3 on 10 is A. To get A, but given B, then it goes to 2 on 5. And that's kind of what I was saying about your total space changing from the whole space to just a selection of B, because B has happened. Anything you want to say more about that, Devon, or should we just move on?
Yeah, let's move on.
Okay, cool. So, problem 1, well, problem 7, but our first probability problem. Tanya plants some seeds. Probability that a seed will produce flowers is 0.8. When a seed produces flowers, the probability that the flowers are red is 0.6, and the probability that the flowers are yellow is 0.3. Tanya has a seed that produces flowers. Find the probability that the flowers are not red and not yellow. So this is this case is actually, well, the flower can't be both red and yellow. I mean, in real life, probably it could, but the problem is actually giving us that the flower is either red or yellow. So the probability that it's not red is going to be some probability, and the probability that it's not yellow is going to be some probability. And in this case, if the probability that so the probability that it's not red is going to be 1 minus 0.6, which is 0.4, and the probability that it's not yellow is 1 minus 0.3, which is 0.7. And now we want to make sure that it's not red or not yellow. So if it's not red, yeah, we can just in this case multiply them, and we'll get our answer of 0.28. Okay, so now we want to complete the tree diagram. So, of course, in a tree diagram, what happens is the columns, they add to 1. So, so does the seed produce flowers? Yes, it's 0.8, and so no would be 0.2, 1 minus 0.8. If the seed produces flowers, then the probability that it's red is 0.6. The probability that it's yellow is 0.3, and the probability that's another color would be 0.6 and 0.3, but 1 minus the sum of those, so it would be 1 minus 0.6, 0.3, which would be 0.1. Okay. So find the probability that a seed chosen at random produces flowers. Red flowers. So we want to find the probability that a seed produces flowers and that the flowers it produces are red. So that probability, well, we first have the probability that a seed produces flowers, that's 0.8, and then that they're red is 0.6, so 0.6 times 0.8 is 0.48, an AND in this case. Now, Tanya chooses a seed at random. Find the probability that the seed does not produce red flowers and does not produce yellow flowers. So basically, if we look back at our diagram, so there's so the seed does not produce red flowers, and it does not produce yellow flowers. So there's kind of 2 cases here. If it produces flowers, then it can't be red or yellow, so it has to be other color, so 0.1. But if it doesn't produce flowers, then that's a probability of 0.2. And these events are mutually disjoint. So yeah, we can add them and we get that 0.28 is the answer there. So yeah, and what's interesting is, in some sense, we have a 0.28 here, and we had a 0.28 earlier as well. And so there was 2 ways of kind of getting to the answer of the questions, which is always a good point to note. Okay, see, 2 of the seeds are chosen at random. Find the probability that 1 produces flowers and 1 does not produce flowers. Right, so the probability that a seed produces flowers is 0.8, and the probability that a seed does not is 0.2. So we have 2 seeds, and we might be tempted to say that it's 0.8 times 0.2, which is 0.16. But it's not true. And one way you can just kind of see an example of why not. If you flip coins, and you flip 2 coins at the same time, what's the probability that you get heads? One gets heads and one gets tails. Well, there are 2 outcomes. Either on the first roll you got tails and then heads, or you got heads and tails. So this is the reason why we need to multiply by 2 in this case to get our answer. So 0.16 times 2 will be 0.32. Okay, so and just to reiterate on the previous point, the issue was that we kind of made a choice where the choice should not have been made in the first place. So you don't really make a choice that that one of the 2 seeds, one of them must be tail. Sorry, that one must be red. It could be either one of them. Okay, so now we have to complete the tree diagram, and the details are that on any Saturday, the probability that Arun plays football is 3/4. On any Saturday, the probability that Bob plays football is 2/5. Complete the diagram. So for, well, first on that side, we have Saturday. So on Saturday, the probability that Arun plays football is 3/4, and the probability does not is going to be 1 minus that, which is, sorry, it's going to be 1 minus that, which is 1 minus 3/4, which is 1/4. But, well, so Arun plays football, and then the probability that Arun and Bob play football is going to be 3/4 times 2/5, which is 3/10. And the probability that Arun plays but Bob does not is going to be 3/4 times 3/5, 1 minus 2/5, which is 9/20. Now the probability that Arun does not play is 1/4, and the probability that Arun does not play but Bob plays is going to be 1/4 times 2/5, which is 1/10. And again, the probability that they both do not play is going to be 1/4 times 3/5, which is 3/20. Right, so now you have to calculate the probability that on one Saturday, Arun and Bob both play football. So we have, again, we have our diagram, and on one Saturday that they both play is going to be this kind of this part of that diagram there, which, so it's just 3/10. Now we also have to calculate the probability that one Saturday either Arun plays football or Bob plays football, but not both. So let me just get the eraser. So yeah, it's always useful to go back on the diagram, because this diagram kind of has all the information you'd really want. So either Arun plays football or Bob plays football, but not both. So if Arun plays, then Bob must. Then Bob. If Arun plays, then Bob must not. So it's this portion here. And if he plays, and if he does not play Arun, then Bob must. So we have this portion here. And then we have to add those two probabilities, which is 11/20. Okay. So now you have to calculate the probability that Bob plays football for 2 of the next 3 Saturdays. So again, now that we have to choose 2 of the 3 Saturdays, there is choice. The way you do it doesn't matter. Well, you know, there is where the 2 Saturdays that he plays football are in the corresponding Saturdays. Actually, well, it kind of does matter, right? But it's not like we're specifically choosing. So it depends on the way you want to look at it. But essentially, we can't make a choice on which one it is. So we have 3 possibilities. Either it's the first 2 or the last 2, or the first and last Saturday. So that gives us 3 possible choices for where when the 2 Saturdays that Bob plays can be. So given that, for each option, we know that the probability is going to be 2/5 times 2/5 times 3/5, which is going to be 12/125. Thus, the total probability is going to be 3 times that. So that's going to be 3 times 12/125, which is 36/125. Okay. Next question. When Arun plays football, the probability that he scores the winning goal is 1/7. Calculate the probability that Arun scores the winning goal one Saturday. So this one is I guess, kind of back to where we talk about events that are independent of each other. Arun playing football. So if he plays football, the probability that he does is going to be, well, I think it's 3/4 from what we remember. And on that day, the probability that he will score on that day, if he assuming he plays, is going to be 1/7. So the probability that Tarun scores a goal on one Saturday will be 3/4. The probability that he plays multiplied by 1/7. The probability that he wins a goal. So that would just be 3/28. Right. So not many questions, I guess. Well, there were quite a few questions, but probability questions in general can be quite straightforward because there's usually not much calculation to them. So yeah, that's for a quick recap. We looked at a few different kinds of rules for probability and how to add them and multiply them in certain situations. Even if you're not given a tree diagram, it could be a good idea to make one because from there you can just read off the information and figure out when you want to add kind of the possibilities in order to answer the question. So yeah, I think that's it from my side. Anything else you wanted to add, Devan?
It's just that when I checked the past papers, I didn't see any conditional probability questions, but I checked our ZNotes and they put conditional probability there. Maybe they put in the syllabus, or I'm not sure. If they actually put in the syllabus, but in case that it comes out well, we got your back.
yeah, remember that formula for conditional probability, then you should be good.
Though it comes
well,
out all the time in AS levels, in AS level statistics. It'll come out all the time.
Yeah, of course. Yeah.
Okay.
Yeah. So let me just finish. For those who are interested in it, you can give it a little try to see if you can use the conditional probability formula we gave you to show that the probability in that multi-hole problem is 2/3 of swapping. So if you swap it, there's 2/3 chance of getting a car. But that's it. Okay, I'm done.
Okay. Okay, I guess that's it. We have nothing else for nothing else. Okay, so thanks everyone for watching today's episode. Wait. Yeah, and come again next week on Wednesday. What's Wednesday? I think it's more on statistics. I think it's histograms and frequency. Yeah.
Okay, cool.
All right, so thanks everyone for watching. Come check out our Instagram page, our website, and also come to our Discord server. Come talk to us, and we'll see you next time. Goodbye.
See you.